Greetings, children. All right, here we go. We got the last two topics, ideal gases and Chem stuff. This is a throwback to the very first day when I told you I won't tell you anything you don't already know. I'm just going to tell you why. The ideal gases is one of those primary examples of this. Where I asked you, if you take a balloon and you get it hot, is it going to get bigger or smaller? You guys all tell me it will. Bigger, very good. So what we're going to do is go from that qualitative to the quantitative, though, and show the reasoning behind these things. So let's talk about ideal gases. Okay, normally I have a whole bunch of demos here for you, but, well, I don't have my equipment, so we're going to have to use our imagination. First things first, what I'm going to do is put the 4 equations that we're going to need for this entire section in one place at one time. These equations, for your future reference, will be P1V1 over T1 equals P2V2 over T2. The next equation will be PV equals nRT. The next one will be 760 millimeters of mercury is equal to 1 atmosphere. And finally, that the total pressure is equal to the sum of all of the other pressures, P1 plus P2 plus P3 plus, and it goes on. These are the 4 equations you will need. Four equations needed for these problems. So I put these all in one spot just for future reference. In your notes, you can go back to one place to look these guys up. We'll talk about them a little bit more as we go along. All right. Let's take a look at gases and what it means to, let me leave there just in case. So, gases. What do you know about gases? What can you remember about gases? What do I remember about gases? Alex, you rose to the top. We've talked about gases throughout the semester. What do you remember? If not Alex, I saw you, Efrain. What do you remember about gases? Anything at all?
They change
What's about that, Frank?
They can change volume, but not mass.
Mm-hmm. Right, they had variable volumes. We'd actually said they will expand to fill their container.
Yeah, no, I'm not speaking.
That also meant with their variable volume, they were compressible. And they had super low densities. Now, all of these will tie into what we'll call the highlights of the kinetic molecular theory of gases. But one of the things I want us to keep in mind is as we look at ideal gases or gases in general, and for us, the gases that we look at will behave ideally. You have to do some pretty heinous things to gases to make them not want to behave. But so when we talk about gases, I want you to think about essentially air or anything else that you work with on a daily basis, because those are behaving, quote, ideally. So it means they behave, they're predictable. So what do I remember about gases? They have variable volumes, they expand to fill their container, they're compressible, super low densities, and they are miscible, right? They mix very well. So what does it mean to be an ideal gas? An ideal gas, just like in the, if we go back to the IMFs, and we were talking about where, actually I think it's in the end of polar. We said, hey, ideally, if everyone were behaving, there we go, everything would be distributed very equally around all the bonds. We could do all that. And that's the ideal world. Then there's the non-ideal world where things go a little weird, right? In our case, we're going to be doing the ideal, doing exactly what we expect these gases to do. Think of them like the representative elements. We know what they're going to do. So ideal gases, when we say that, it just means they do what we think they should do. That is to say, i.e., as a gas gets hotter, it gets bigger. We know this intuitively. All the gases we're going to talk about will do such things. So what I want to do is qualitatively now talk about what it means to be an ideal gas and some of the tenets of the, quote, kinetic molecular theory of gases. So let's go highlights. Of the kinetic molecular theory of gases. I'm going to highlight some of the important ones for us to sort of know. Now, the kinetic molecular theory of gases, as the name implies, kinetic, these things are moving. We're talking about moving molecules, kinetic molecular theory, our best explanation of gases. So this is our best explanation of how these moving gas particles behave. So the highlights of these guys. 1, gases are mostly empty space. That's kind of a no-brainer. Clearly, we're breathing a bunch of air. We're looking through air right now. We can see forever through air because most of it is empty space. Sometimes we have to state the obvious, though, to get anywhere else. We have to start from a reference point. This reference point says, when we're looking at gases, they're mostly empty space. As such, we also have to say a couple of other things. Gases have no affinity for each other nor their container. They do not want to interact. They do not want to interact with each other or the container, which means they don't stick. If they happen to run into each other, which is like statistically like not going to happen, or every time they decide to hit some sort of surface, they have no desire, no impetus, no incentive to sit there and stay there. They're going to bounce away and go their merry way. They don't want to interact. Now, this is kind of important. If you think about it, gas molecules are whizzing around at all times. Eventually, they're going to hit something. If they wanted to hit something and stick, we actually have a name for that. When they decide to hit something and stick, we have a couple of names depending. What happens when a gas goes from a gas to a liquid? We call that condensation. Or if it went straight to the solid, we're talking about it depositing. If these molecules wanted to interact with each other, if every time they hit each other, they would condense. If they wanted to hit the solids and go like, oh, I'd rather stay here, they will condense out. And that would be a bad day for us because all of a sudden, all of our air that we breathe would not be flying around. Gases. Gas molecule collisions. Are completely elastic. What does that mean to be completely elastic? What does elastic mean?
Well, it means like if they stretch, then they go back
Right. What are you thinking of when you say that?
like a rubber band.
Exactly, right? So immediately when I say the word elastic, you think rubber band. That means if I stretch it, it goes right back to where it was. When these guys hit something, they go right back to what they were doing. You might think about billiard balls, except they don't slow down. All right, gas molecule collisions are completely elastic. They do not lose energy. They do not lose energy when they hit something. Why is that important? If they lost their energy, if they slowed down their energy, what would happen to them? Let's go back to some of our earliest definitions. What was that official definition of temperature that I had to give you? I always want to give you the easy ones, but I had to give you the formal one, and this is the reason why. At the very end of all things, I need the formal definition of temperature. What was that?
The speed at which stuff is moving.
I believe I heard you say the average kinetic energy.
Yeah.
Yeah, so exactly. Temperature is the average kinetic energy. If they lose energy, that means their temperature is going to drop. If their temperature drops, eventually they will condense. They'll turn into a liquid. And while it's kind of fun for 9 months, I really don't like breathing in liquid anymore. So it's important that these gas molecules, when they hit something, don't lose energy. You know, when I said gas molecule collisions are completely elastic, I said, think about billiard balls. They hit something, they bounce off. Well, they slow down, right? They have the friction of the table to slow them down. Gas molecules don't have that friction. They just keep going. Finally, gas molecules travel in straight lines or in straight paths. Now, why might that be important? Imagine that you had a whole bunch of oxygen molecules racing towards your face, and they decided, I kind of really don't want to go in there, and they just decided to go their own way. That would be bad. Imagine all the gas molecules like racing towards you and deciding, I don't even want to hit that person in general, and they just like move out of the way. That would be bad. That would be weird. It would create a vacuum. Nature abhors vacuums. It likes homogeneity. Gas molecules, wherever you're traveling, that's the direction you're going to go. How do you change directions? Hit something. Otherwise, that's how you're going. Now, the interesting thing about gases is that we've actually known a lot about gases relatively. We knew more about gases before we knew about temperature. And I'll show you why. When we talk about gases, basically the only and best and only way to talk about gases is to look at the pressure they exert. Okay? You can try to measure their volumes and everything, but the first way they ever understood gases was by their pressure, and it is still how we do things. We measure their pressure. So let me ask you something. So we define, let me get that in another color. Let's go blue. We define gases by their pressure. So my next question is, what is pressure? What is pressure? Besides what you're feeling every time I decide to ask you guys a question, you guys look nervously around your internets left and right to hope that someone else is going to answer this question. Meanwhile, the mounting pressure just keeps going until you finally have a psychotic break. What is pressure? Nobody?
It's a force being exerted on something.
Yeah, can you actually think of any units of pressure for me, Miguel? Do you know how pressure is defined?
I can't remember right now. I used to know.
PSI.
Does anybody?
PSI.
PSI, right? What is pressure? PSI, right? If you're doing any bicycle riding or filling up your car tires, it'll say inflate to this many PSI. What is PSI? You ever thought about that?
No.
Pounds per square inch. That's what that means. I bet a bunch of you just learned something there.
Yep.
So PSI is pounds per square inch. Pounds. What other units do those remind you of? Well, let me just, yeah, it reminds you of grams, right? It reminds you of a mass. Now, in this case, it's technically a pound force. And so oftentimes they'll put in a pound force. This is a force of gravity on the mass. What does inches squared look like to you?
Distance?
Inches squared is an area. So what is pressure? Pressure is merely a force over an area. The force over an area. So that's where you get your so-called PSI, your pounds per square inch. You also have the Pascal, which is a Newton over a meter squared. Both of these indicate a force over an area. There are other units of pressure. So if you're going on into physics at all, you'll learn the Pascal. In physics engineering, Pascal will be one of the things you do. Other units of pressure will be atmospheres, abbreviated as ATM. You'll have bars. You will have, what's another good one? Torr and millimeters of mercury. All of these you may, if you go on in your scientific career, you'll probably see one of these in one form or another. And in fact, you guys have all seen the units of bars. Can anyone think of where you might have seen the word bar beside a place to drink? The barometer. If you ever listen to the weather person and they'll talk about the barometer rising or falling, let's check the barometer. They're looking at the pressure in the atmosphere at that moment. Now, atmospheres, that seems like a standard thing to say, like, oh, we have atmospheric pressure. What is the pressure? The same as you feel in the atmosphere right now. Pounds per square inch, that's a force over an area. That's English units. We have pascals, which is a Newton over a meter squared. That is still a force over an area. So Newton is a measure of force over an area. There are actually a few more other measurements of pressure out there, but really for this class, we're going to be looking a lot at this guy and this guy. That shouldn't be any surprise. Right? We will also be briefly talking about Torr. Now, in any normal semester where I had you guys sitting here, I would demonstrate what pressure might look like by taking my open hand and leaning against one of the students. Miguel, you're my student. I'm going to take my hand and I'm going to lean against your shoulder. Do you feel a pressure on your shoulder?
Yes.
Yes. Now what I'm going to do is, instead of opening my palm, I'm going to put my fist like so. There's I hope you guys can see me here. So instead of my open hand like this against Mr. Miguel, I'm going to take my thumb and press into your shoulder, Mr. Miguel. Do you feel more or less pressure?
More.
Yeah, absolutely. Did I lean on you any heavier?
No.
No. What did I do? I shrunk down that area. And by shrinking down that area, I have now increased the pressure. When I take this area and I make it smaller, the pressure will go up. It's a force over an area. Now, that's okay. I mean, if you think about the pressure idea, if you want to get rid of the pressure, spread it out. Spread that force out as far as you can go. My question is now, if we define everything by pressure, how is pressure defined? Or how is pressure measured? We know now that it is a force over an area, but how do you actually measure that? All right, here we go. A little history lesson. All right. In 1643, or at least that's when he decided to publish this, there was a guy named Torricelli. He played with mercury. Specifically, this is what he did. He took a bucket He took a tube and he filled it full of mercury and upended it into a bed of mercury. And he noticed something very peculiar. The mercury stayed inside the tube. It did not fall out. He took this tube and he started making this tube taller and taller and taller and filling it with more and more and more mercury. And he noticed that until he got to 760 millimeters tall, the mercury would stay in the position that he put it. So if he only had a height of, say, 200 millimeters, it would stay there. If he had 400 millimeters, it would stay there. As soon as that height of mercury got above 760 millimeters, it would start to fall out of the tube. But it would only fall until it got to the height of 760 millimeters. Now, why would it do such a thing? Why would this difference in height be 760 millimeters and never change? Let's take another step on this. Can we agree that gravity pulls everything down?
Yeah.
Yeah. Can we agree that gravity wants to pull that thing down?
Yep.
If that mercury falls out, can we agree that it wants to now make the mercury level rise?
Yes.
If all of this mercury falls out, is it not going to make this rise up?
Yeah, it will.
Of course, but it doesn't. So what is preventing it from falling out and filling up that pool of mercury? For every force, there has to be an equal and opposite force if nothing is going to move. So what is putting this force? What is putting this pressure on the outside to say, no, you can't come out?
The mercury already in the bait, in the bucket.
It doesn't care. It'll fill up the whole container if it wants. Remember, liquids want to fill their container, so that's not the problem.
The air that's in the tube.
Actually, the air on the outside, and it's the lack of air on the inside. And I'll explain that in just a minute. Right, this whole idea is that we are talking about ideal gases. We're talking about, in this case, the air molecules are pushing back down. So those air molecules are pushing down on that pool of mercury, and until I get enough in the tube to have enough force to go against that air, that mercury is going to stay inside. Now, as long as it was less than 760, that height wouldn't change. As soon as he got to 800, 900 millimeters tall, that mercury would fall down until it hit 760, at which point the air molecules have successfully pushed hard enough to keep it up at that height. Hence, this is why 760 millimeters of mercury, a height scale, equals atmospheric pressure. This is why we wrote 760 millimeters of mercury is equal. Now, for anybody who's listened to the weather person or heard any weather forecast, they will often talk about the mercury is rising or the mercury is falling. What do you think they were referring to? When I was a kid, I thought they were talking about the mercury in thermometers. Of course, if the mercury is rising, it's going to get hot. If the mercury is falling, it's going to get cold. What I didn't know is that they're not talking about the temperature. They're actually talking about the pressure of the air coming through. And the higher the pressure, the higher the temperature. Anybody here from the Midwest or maybe North Carolina?
Yes.
Yes. Have they not talked about a low pressure front coming through before?
Yes.
And what does that usually mean? It's going to get cold. And if you're lucky, you'll get a thunderstorm. Yeah, low pressure front coming through. Low pressure is coming up. What that means is if the pressure outside goes down, if it is not as strong, then gravity starts to win and this column starts falling. A high pressure system comes through. We just had one last week, right? High pressure system comes through, more pressure on the outside, this is going to go up. So what the weather people are looking at is this difference in pressures coming through. I mean, this is what's making the winds blow, right? They're watching these things because they will be indicative of the weather patterns. They'll be indicative of the temperatures, which will follow this pressure. So when they talk about the mercury rising and falling, they're actually talking about the pressure inside the barometer. Oh, the barometer, barometer. That's what he made. Now, it should be noted that Mr. Torricelli is the guy that basically gave us the way to measure the pressure of gases. And of course, if you're really cool, you get to put your name on it. So 1 millimeter of mercury, he said that's going to be equal to 1 torr in honor of me, Mr. Awesome, for figuring this out. So of course, then that means 760 millimeters of mercury equals an atmosphere. Also 760 torr equals 1 atmosphere. What's interesting, I don't think, let me just, I always love these little pieces of history. You go like, oh, wait, what? This number, 1643, does that strike you as odd in relation to any of the other history lessons I have given you in this class?
It's a lot older, like way back in the day.
Say it again, Sonia, you broke up.
I'm sorry, I'm having a bad internet connection today. It just seems like a lot older, like it's not as recent as the other ones.
Yeah, that's exactly right. It is a lot older. And in fact, I think when we were doing the conversions or was it with density? Oh, it was in the density one. At the very end of density, we talked about temperature and how hot or cold something is. We didn't know about temperature for like another 100 years. We had no way of measuring temperature, but we could measure the pressure of things. To me, that seems almost backward. Like, how do you measure pressure? Well, you need a gauge. How do you make a gauge? Like, I don't know, but at least you can make a thermometer, right? No, they had a way of measuring the pressure before they had a way of measuring temperature. I don't know, that just is kind of an interesting little tidbit to me. All right. Let's do some qualitative talk. Okay, for these, we're going to be looking at the individual gas laws. Now, these individual gas laws were devised by 4 different people who started noticing funny phenomena. Now that they can actually measure stuff that we intuitively know, they decide to, well, start measuring it. And as they start measuring it, they start noticing that the behavior of the gas follows a natural law. Hence why they're called gas laws. This isn't a theory. This is what happens. Now, these each individual gas laws, eventually at the end, we will combine them. You do not have to know them individually, but it is kind of fun to look at, in some respects, just how easy it is to get your name on something. Did somebody just write on my screen? I think they did. All right, first up, Avogadro. Remember this guy? Yep. Not only did he give us that cool, useful, useless number, he was also the first to give us an ideal gas law. So what is he going to do? He's going to keep temperature and pressure constant. He's going to look at moles, or I should say volume versus moles. Volume is the dependent. Volume versus moles, right? Of course he's going to use moles. Of course he's going to use the amount of something. He's the master of discovering the amounts of things. So here it goes. As the moles, the amount of gas increases, what's going to happen to the volume of that gas? Will it go up or down? If you put more stuff in there, does it get bigger or smaller?
Bigger.
Of course. Listen, right now you guys know all of these answers, okay? Avogadro is going to keep temperature and pressure constant. That's pretty easy. You just take a balloon. You sit in your room. Is the temperature of your room going to change? No. Is the pressure of your room going to change? No. You put more stuff in the balloon. Does it get bigger? Yes. Now, it turns out it's directly proportional. You double the moles of gas, you will double the volume. But he was the first guy to actually sit down, do the experiments, and prove that. Everyone sort of had an idea, but they didn't have the numbers to prove it. So he proves it, and guess what? He's already got a number. He might as well put his name on a law while he's at it. He will also keep the volume and temperature constant. And he's going to look at pressure versus moles. Oh, I guess we could also say vice versa, right? Up here. If you take moles out, the volume will go down. But he's going to say this, as the moles, as the amount of gas, as I put more and more of it in there, what happens to this pressure? Does the pressure Oh, absolutely. The pressure will go up. If you give it no room to expand, if you keep that volume constant, if you give it nowhere to go, that pressure is going to go up. We all know this intuitively. He was just the guy that put the numbers to it. He says, look, if I double the number of moles of gas, I will double that pressure. And he did the numbers. He did the experiments to prove it. So guess what? He gets to put his name on that. We know this. And it's pretty easy to do this experiment. You just take a rigid container and you just keep shoving stuff in there. We've all done this. As you pump up your bicycle tire, if it's completely flat, it'll start expanding and expanding and expanding. And eventually that tire is stretched to its utmost. It will not change its volume anymore. You keep putting more gas in there, the pressure inside your tire goes up. We know this. All right, listen, if Avogadro can do this, other people go like, I want my name on something too. I'm gonna go ahead with this very sophomoric intuitive thing. I'm gonna do the experiments. I'm gonna prove something, get my name on it too. Enter Boyle. Boyle's law. Sometimes, guys, it's just this easy to get your name on something. You just gotta be first. He is going to keep constant moles and temperature. And he's going to look at volume versus pressure. So, how hard is that? He's going to keep the moles, the amount of gas, constant. That's pretty easy. You just take a container and you seal it up. He's going to raise the temperature. Or, sorry, keep the temperature constant. That's pretty easy. You just sit in your room. What he's going to look at is volume versus pressure. So he's going to change the pressure on this gas. So you can think of it in terms of a balloon. He's blowing up a balloon. He's tied off the end. No gas goes in. No gas goes out. Keep the temperature constant. That's pretty easy. Just leave in your room. As the pressure on that balloon increases. So he puts it in some sort of chamber and just starts putting pressure and pressure and pressure on that balloon. Is that balloon going to get bigger or smaller? You take a balloon and you put a whole bunch of pressure on the outside of it.
Gonna get smaller.
It'll get smaller, absolutely, right? You're trying to compress this thing, and we always said gases can compress. That's pretty easy. He noticed that if he doubled the pressure, that volume got cut in half. He did a series of experiments that continued to prove this correlation, this inversely proportional relationship. We all know this. How do we know this? Can anyone give me an example from their normal everyday life where you have watched the pressure change and the volume change of anything? Anybody here ever drive to Lake Tahoe? Anybody have a bag of potato chips in their car? Anybody had that potato chip bag explode?
No.
No. Oh man, you're not living life. Yeah, it's a wild thing. You take a bag of potato chips. I want you to do this one time. You're gonna drive to Tahoe. Take a bag of potato chips. Look at it. Drive up the Tahoe. By the time you get up there, that thing will be bursting at the seams. Sometimes it explodes and makes you think you blew a tire. That's always fun.
I bet.
Why did that bag get bigger? Because the air pressure up in Tahoe is less than it is down here. And so the pressure on the outside of that bag goes down, the volume got bigger. Not to be outdone, other people are jumping on this bandwagon of like, really, it's that easy? All I have to do is this? My goodness. Now that I have ways of measuring temperature, let's go for it. Okay, you got Charles' law. So there's this guy named Charles. What he does is he's going to keep constant moles and pressure. He's going to look at volume versus temperature. Okay. We've done this one before. As the temperature increases, the volume will increase. You get that balloon hot, right? You're gonna take the balloon, blow it up, tie it off. No more gas goes in, no more gas comes out. Keep the pressure constant. That's easy. You just do it in your room. Now I'm gonna heat it up. Oh, look, it got bigger. But he was able to correlate. If you double that temperature, you will double that volume. He saw that direct proportionality to it. Once he proved that, he gets to slap his name on it. All right. So let's see, volume versus pressure. Potato chip bag. Potato chip bag Tahoe. This guy, hot air balloon. If you've ever had the chance to watch one of those operators heat that thing up, they just start throwing hot air in there. That balloon just magically gets bigger. And the last one we have here is, I don't know if it's Guy or Guy Lussac. Guy Lussac. All right. He notices the last variables that have not been touched. He's going to keep moles and volume constant. He's going to look at pressure versus temperature. Okay, as the temperature increases, as I heat a container up, and it's pretty easy to do this, you just take a rigid container, put a bunch of gas in it, cap it off. I heat up that container. Does the pressure increase or decrease?
Increase.
Of course it gets bigger. The pressure will go up, vice versa. Can you think of anything in your daily life that would be an example of this?
When a soda gets hot.
Say again?
Like when a soda gets hot, pressure increases.
Okay, yeah, when a soda gets hot, the pressure increases. Anybody else?
What about like heating up a tea kettle?
Right, you get the tea kettle hot and the pressure inside gets hot. Pressure cookers, right? Pressure cooker or spray paint can next to hot water tank, hot water heater. Why do they tell you not to do that? Because if you get that thing hot, it's gonna explode. Now, each of these individual gas laws, once they were sort of put down and people could start working with them, they realized that each of these by themselves is really cool and clever, but there's a link between all of them. And so what people did is they ended up combining them together into a so-called combined gas law. So combining them all, this will lead to the combined gas law. And that looks like P1, V1, oops, hold on. Oh, look, my pen's gonna not work. Wake up, pen. Here. If the pen doesn't work, then we're gonna have a bad day. All else fails, take the battery out, put the battery back in. Maybe it restarts itself, I don't know. There we go, P1, V1 over T1 equals P2, V2 over T2. Inside of this gas law right here are all the other gas laws. Now, I will not worry about changing the number of moles. Technically, there should be an N at the bottom underneath the here and here, but I'm not going to do that for this class. Maybe if you come to Chem 120, we might play with that. But I'm going to keep it simple for us. Now, P1 V1 over T1 equals P2 V2 over T2. Can anyone think of what these symbols might be? What is P?
Pressure.
Pressure. V?
Volume,
Volume. And of course, T is now
temperature.
temperature. I must point out, for these problems, pressure and volume can be anything. Temperature is always Kelvin. What do the 1 and 2s refer to?
Before and after.
Yes. 1 and 2. This is before and after. It's just a way for us to differentiate between the two pressures or temperatures or volumes that we're looking at. Now, we've done a lot of qualitative stuff up here. The feel-goody, yay! Let's put some numbers to this stuff. Let's actually use these. For the problems I'm going to do here, I'm going to be using the ideal gas law for quite some time. And I'm going to go through it and run through a series of problems that you would see. And what I want us to do is to think about the fact that for a lot of these, up until we get to the final end, we can use our intuition that we've just been doing up here to get an idea of what the answer might be before we even plug any numbers. Eventually, we'll just have to use this outright and trust our math. I will also preface the rest of this that I'm not going to solve these for you. If you need the math to help solve these equations, I'll hang out after class and show you the math behind it. What I will do is skip to the ends of each of these solvings. So, without further ado, let's do some problems. All right. Let us do some problems, right? This is now the quantitative. Now we go away from the feel-goody. Of course we know this. Now let's put some numbers to it. Okay. if a 4.35 liter sample of hexane gas is at 1350 millimeters of mercury, and it expands to be 7.45 liters, what pressure did this? Okay, you have a balloon. You tie it off. You're like, oh, it's 4.35 liters. You're looking around, you say, oh, this is the pressure. Okay. You close your eyes, you open your eyes, and this balloon got bigger. You're going to go back and measure the pressure. What should that pressure be? Now, for the ideal gas questions, what you want to ask yourself above and beyond anything else, first and foremost, is, are the conditions for this gas changing? Because if they are, you're going to want to use an equation that changes from one state to another. Now, pro tip for the next 6 or 7 examples, yes, they will be changing. But I always want to do this just like I do with all of our conversions, where I ask, where are we going? Is there anything that looks like there? We're always going to ask all the questions so we get used to the methodology. All right. We have a 4.35 liter sample. It's getting bigger. Do the conditions on this gas change? And Bella says yes. If that is the case, then you want to write down P1 V1 over T1 equals P2 V2 over T2. Is there anything I did not talk about or that remains constant?
Temperature.
That is correct. So we have no temperature. If there's no temperature given, you have to assume that it is constant. If it shows up on the left and shows up on the right and they're the same value, we get to get rid of them. So we can simplify this to be P1 V1 equals P2 V2. Let's go back up in there and let's take a look at what we have. We have a 4.35 liter sample. That is a first volume, and it is held at a first pressure. At will tie those two things together, just like of will tie two things together. It's going to expand to a V2. So what is the new pressure? That's what we're looking for. So we're going to solve for P2. P2 is equal to P1 V1 over V2. And now we plug and chug. Pressure one is 1350 millimeters of mercury. The V1 is 4.35 liters. The V2 is 7.45 liters. Liters will cancel. We're left with a pressure like we wish. Now, before we actually punch in our calculators, let's do some intuition. We just watched this balloon go from small to big. Will the pressure have increased or decreased to allow this to happen?
The balloon.
I think Maria said, say it again.
Decrease?
Yes, it's got to go down, right? We have to let that pressure off of this balloon to let it get bigger. So if we've done this correctly, our pressure will drop. Did anybody decide to go ahead and do the numbers? Are you just waiting for me?
In the process.
I heard 788 millimeters of mercury. It went down like expected.
Correct.
All right, how are we doing? Are we okay so far?
Good.
These problems, as long as you set them up correctly, as long as you label everything correctly, these should be easy points. These should be like boom, 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 done. So when you get to these on the final, it should be like, oh, it's one of those? Oh, I got this. A 225 milliliter sample of argon gas is compressed from 2.31 atmospheres to 6.32 atmospheres. How big is it now? You got a sample of argon gas. It's a certain size. You take it from 2.31 atmospheres to 6.32. Is it going to get bigger or smaller? Pro tip, compressing.
Yeah, smaller.
Yeah, it's going to get smaller. All right, but let's have our intuition match everything else. We ask ourselves, are the conditions changing? You will say, of course. P1 V1 over T1 is equal to P2 V2 over T2. Is there anything I didn't talk about or that remains constant?
Temperature.
That's correct. No T, so let's take it out. So now we have P1 V1 equals P2 V2. Let's go back up and make sure we know what we're looking for. We have an initial volume that goes from one thing to another. So this should be P1 going to P2. And when I say how big, we're looking for that V2. Now, again, it's important to read the problem carefully. Make sure you're labeling it correctly. Make sure you keep the ones with the ones and the twos with the twos. So we're going from one pressure to another pressure. So make sure you get those labeled right. It's not always 1, 1, 2, 2, so be very careful. We're going to solve that for the V2. So V2 is equal to P1 V1 over P2. And now we plug and chug. P1, 2.31 atmospheres. V1, 225 milliliters. P2, 6.32 atmospheres. Our pressure goes away. We're left with the volume like we wish. We expected it to go down. We expected it to get smaller. Does it indeed get smaller? What'd you get?
I got 82.
82 milliliters. That is indeed smaller, just like we anticipated. Easy peasy? Giselle, easy peasy, or did you just pop in?
I just popped in, I'm sorry.
Okay, that's fine. Bosma, did you just pop in, or?
Yeah.
Okay. Well, then just say yes. This is totally easy.
Easy.
Nah, I'm not going to give you that. Thank you, Giselle. All right. So I'm going to try not to sneeze over here. So I'm going to fail. Hold on. It's a good thing I'm wearing my mask. I'm just kidding. I'm all alone in this room. All right. Thank you. All right. How about this? A 10.2 liter balloon of hydrogen gas. Goes from a room. Goes from a room at 278 Kelvin to a room at 329 Kelvin. How big is it now? Okay. Are the conditions changing?
Yes.
Yes. Yes. So we're going to write P1 V1 over T1 equals P2 V2 over T2. Is there anything I did not talk about?
Yeah. Pressure.
Yeah, right. I don't see any pressure. Get rid of it. So V1 over T1 is equal to V2 over T2. Go back up to this problem. I've got a V1 that is at a T1. Remember, at will go to a room. I go to, which means I'm going somewhere else. I'm going to go to a T2. How big is it now? Okay, solve this for V2. V2 is equal to V1 T2 over T1. Before I even plug and chug, is this balloon going to get bigger or smaller? That's right. Bigger. Right, we're increasing that temperature. We're getting it hotter. It's going to try to get bigger. So let's see if we're right. So V1, we said was 10.2 liters. T2 was 329 Kelvin. T1 was 278 Kelvin. Kelvins cancel out. We've got a liters like we want. 12.1 liters. That's bigger, just like we want. Guys, okay?
Yeah.
Preguntas? Alan, you okay? How's this looking?
Looks good.
Bro, we got a good thing going on. You good? Isaiah, you okay? I assume so. Julio? It's awfully quiet. Want to make sure I got everybody.
Mr. Quinlan,
What?
we always keep the units the same, right? So
Yes. So
it's going to be milliliters.
go ahead. Go ahead.
So if the problem says, you know, milliliters or microliters, it's going to be whatever it says in the problem.
Yeah, so far, you'll notice that I haven't really talked about units because I have kept the units in such a way, if you notice, they all cancel out. They should. That's what I've told you from day one, all we care about are units, right?
Mm-hmm.
So as long as the units work, we don't care, except temperature is always in Kelvin. That must be.
If the problem has the temperature in Celsius, do we convert it to
Hey, I'm
Kelvin?
glad you asked. Ready? It's like I've done this before. Here we go. If a 14.75 liter sample of nitrogen gas at 25 degrees Celsius shrinks to 8.91 liters. What temperature did this? Okay. Do conditions change?
Yeah.
Yeah. So we write P1 V1 over T1 equals P2 V2 over T2. Anything I didn't talk about?
Pressure.
No pressure, so let's simplify that to V1 over T1 is equal to V2 over T2. Go back up to your problem. Got to take a look and label these things. I have a 14.75 liter sample. That's going to obviously be my V1. It is at, remember they're going to tie it to it, a T1. It's going to shrink 2, which means we're going somewhere else. A V2, so I'm asking, what is that second temperature? So I'll solve it. T2 is equal to V2 T1 over V1. And now Maria is going to tell me, hey, we're going to have to do something. What's V2?
Oh, sorry. 8.91.
8.91 liters. What is T1? Now, you were the one that said we can't do the 25, so I'm glad you sort of like paused. That meant to me that you weren't just looking at that temperature and going to put it in there. You were looking for a way to convert it back to Kelvin. You must do this in Kelvin. Let me, let's see, what are we? What did it, wait, here we go. I need to know this. Oh, look, you still need to know it. And this is why. All right. So we got the 298 Kelvin. We're going to go ahead and put our V1 on the bottom. That was our 14.75. By the way, before we even do this, the balloon shrank. Did the temperature go up or down?
Down.
Had to go down, right? All right. At the end of the day, our volumes are gone. We're left with the temperature. And if you do this, you get 180 Kelvin. Which, let's put it back into things that we can talk about. Negative 93 degrees Celsius. And yes, it still behaves. Nitrogen behaves for quite some time. To answer your question, Maria, yes, you want to get back to units that make sense. However, since it's multiple choice, the answer will be obvious. I'll either have them all in Kelvin and you just choose it, or I'll have them in Celsius and you have to go from that Kelvin back to the Celsius to find your temperature.
Okay, thank you.
You're welcome. It's almost like I've heard this before. Why always convert to Kelvin? All right, I'll do this por ejemplo. A 10.0 liter balloon is brought. It's brought from inside the Antarctic Research Station to the outdoors. If the temperature inside is 23 degrees Celsius, the outside it is negative 40 degrees Celsius. How big will the balloon be? One of my longest prompts there. Those are actual real numbers. I love doing stuff with real numbers. I have a balloon, it's 10 liters big. I'm going to take it from inside to outside just to see what happens. First of all, will it get bigger or smaller?
Smaller.
Smaller. That's right. How small?
A lot. Smaller.
Let's do the way. We know that it's going to change. We got P1 V1 over T1 is equal to P2 V2 over T2. I didn't talk about pressure, so this becomes V1 over T1 is equal to V2 over T2. I have a 10-liter balloon, V1. It goes from a T1 to a T2. How big is it going to be? It is equal to V1 T2 over T1. If I plug and chug this the wrong way, right? The wrong way is using degrees Celsius, not converting to Kelvin. I would have my 10.0 liter balloon. I would have my T2 at negative 40 degrees Celsius and my T1 at 23 degrees Celsius. If you plug and chug that, somebody just divided by 0. What does it even mean to be a negative volume? Is that even possible?
Folded in on itself. The black hole now.
If I'm asking the question like that, it's almost rhetorical, and the obvious answer is obvious. No, it cannot happen. You can't do it. And this is the reason why we have the Kelvin scale. Because we can't be working with negative numbers. It makes no sense to go negative. Scale. So let's do the right way. Okay, is equal to V1 T2 over T1, but now we're going to convert everything to Kelvin. So I have my 10.0 liters, but now T2 is 233 Kelvin, whereas T1 is 296 Kelvin. If you do this, you get 7.87 liters. Much better. Now, I do want to point something out. When we talk about the fact that they say, if you double the temperature, you double the volume. You have to do that in Kelvin, which means gases will expand, but not kind of like you think. It takes a lot of temperature to make those guys really expand. You have to really, really heat that stuff up. Here, we're not going up double. Double of 233 is 466. We are far away from that. When we're talking about that in temperature, we're talking about it in terms of kelvins. All of these problems for the ideal gas are essentially plug and chug once you set it up correctly. How are we doing? Is everyone doing okay? Can't tell if I'm going too fast or not.
I'm good.
Brenna, you okay?
Yeah, I'm good.
All right, everyone's. Carla,
I will be okay. I have to step away for a little bit, unfortunately. But thanks for checking. I'll be okay.
oh, okay. Well, yeah, I think at the end, if you watch the little segments or start the homeworks, I think a lot of this guy is really, the ideal gas laws are fun, for me at least, and these are going to be some really easy points that are just, I hate to say it, but plug and chug. But what it does allow us to do is take our intuitive, qualitative understanding of gases and now put numbers on them. We can quantitatively analyze them. Let's do at least one, two, at least 3 more. We'll see where our time is. And maybe I'll just finish this up tomorrow or something. I just want to get these last 2 or 3 in. A gas in a rigid 500 milliliter container is originally at 1.23 atmospheres and if it is heated to 100 degrees Celsius, what is the pressure now? All right, we got a gas in a rigid 500 ml container. It's originally at 1.23 atmospheres and 25 degrees Celsius. If it's heated to 100, what is the pressure now? Are conditions changing? Yes. What do we write? P1 over T1 equals P2 V2 over T2. This should become just the mantra at this point. Is there anything I didn't talk about or remained constant?
Volume.
Volume. I gave you a volume, but I didn't give you a second volume. That indicates it didn't change. A. B, I said it was rigid. It's stiff. It's not going anywhere. There's no volume. So this is now P1 over T1 equals P2 over T2. So, and also ties things together, right? So we have a P1 and a T1. We're going to T2. What is that P2? So P2 is equal to P1 T2 over T1. Is the pressure going to go up or down, guys? Apparently, you guys all know the answer. Get it? Hashtag dad joke. Sorry. I'll be quiet. All right, let's plug and chug it. So we have P1 of 1.23 atmospheres. We have our T2, which is 373 Kelvin. Emphasizing that we have to do that. Got to get in there. Divided by our 298 Kelvin. Again, Kelvins cancel. We have atmospheres like we want. So it looks like we quadrupled the temperature. We did not. We did it in Celsius, but not in Kelvin. This 1.23 rises to a mamma jamma 1.54 atmospheres. We got a pretty stinking hot pressure. All the way to the end. Let's do N. A sample of gas at 232 torr and 130 degrees Celsius is heated until the pressure rises to 1239 torr. How hot is it? At this point, we're still on our broken record. Of course, the conditions are changing. We see a couple of pressures there, they're changing. So we get a P1, V1 over T1 is equal to a P2, V2 over T2. Let's see, what did we not talk about? We didn't talk about the volume, so we can get rid of it. So we get P1 over T1 is equal to P2 over T2. We'll look at the problem, look for the words that bind things together, and we've got a P1 at a T1. It's going to go 2, that means the second set of conditions. A P2, and we're asking, what is the second temperature? So T2 is equal to P2, T1 over P1. All right, so before I even get there, you had this sample, the pressure increased. Did the temperature go up or go down? That's right, it went up. Let's see if our math pulls it out. So P2 is 1239 torr. T1 is 403 Kelvin. And our P1 was 232 torr. 4. First cancel, we got a temperature. So at the end of the day, that meant T2 was equal to 2152 Kelvin, which will convert that to 1879 degrees Celsius. Wow, that's pretty hot.
I have a question.
I have an answer.
So when you did the T2 equals P2 over T1 over P1,
Mm-hmm. How did I do the math?
No, I'm confused on why it won't be P2 plus P1 over T1.
Math. So what I'm gonna do is I'm gonna cut out early. So I'm gonna stop the recording here pretty soon, and I'll actually go through the math with you because you're not the only one who needs that math refresher. So I'm gonna go ahead and do that here. I think what I'll do is I might as well just do it now because it's a slightly newish topic to go on the ideal gases. Slightly newish right after this, where we actually combine everything together. But judging by everything, I think brains are kind of full at the moment. So I'm going to stop here and then I'll answer your question about how the math goes. Is that cool?
Yeah, thank you.
Cool. All right.